Okay, so the last tool I want to quickly introduce before Sean takes over is geochronology. And there are many different types of geochronometers, but here I've just listed some of the most widely used ones in tectonics. And they fall into two categories: radiometric techniques, in which radioactive elements are incorporated during growth or recrystallization of a mineral, and then once they're incorporated, they start to decay to their daughter product. And radiometric techniques resolve time by comparing the ratio of radioactive isotope to the daughter product also present in the rock. And these are all techniques I've listed here that I'm sure you've heard of. Uranium lead is very commonly used, typically on zircon. But more recently, as analytical precision has improved, it's applied to other uranium-bearing minerals such as titanite, apatite, even calcite. And then uranium thorium or U series dating applies to calcite and is commonly used to date corals or speleothems. Potassium argon and a related more robust technique known as argon-argon is applied typically to micas, both biotite and white micas, sometimes other minerals like amphibole and feldspar. And rubidium strontium, again, applied mostly to micas, but sometimes used with multiple minerals to produce isochrons that help determine whether mineral pairs are in isotopic equilibrium. Then the second category is non-radiometric techniques that do not involve radioactive elements. Some forms of cosmogenic dating, which is a near-surface exposure age technique that dates the timing over which materials have been bombarded by cosmic rays close to Earth's surface. Many of these techniques focus on stable isotopes that don't decay. Magnetostratigraphy, a relative dating or correlation technique focused on the patterns of secular change of reversals of Earth's magnetic field. And finally, incremental dating techniques, which are sometimes qualitative, but that allow year-by-year annual chronologies based mainly on how organic materials such as trees or things like lichen grow over time. A few caveats to keep in mind when considering radiometric dating techniques, which are the ones most commonly applied in tectonics. We use the term geochronology rather than thermochronology to indicate the timing of crystallization and not cooling. That crystallization can occur in different ways. For example, crystallization from melt, such as the cartoon on the left. That's one of the simplest forms of crystallization. The radiometric clock starts as soon as the mineral crystallizes out of the melt. And it's common for things like zircons or other igneous minerals to have these nice zonations to them, with older ages preserved in the core and younger ages on the rims, therefore sort of bracketing the timing or duration of crystallization within that melt. Another form of crystallization that can start the radiogenic clock is metamorphic overgrowth. So the cartoon in the center is showing a zircon grain with an igneous core that then has a more cloudy metamorphic overgrowth formed when the rock was reheated and when new zirconium was provided to grow new zircon. A common source for this zirconium is the breakdown of garnet, for example. And then a third form of crystallization that can restart the clock, so to speak, is deformation-related crystallization, like the diagram on the far right, where old grains deform and produce new, finer grains with newly developed isotopic compositions. So deformation-induced recrystallization is also something geochronometers can capture. Note that this dating of crystallized products contrasts with what is called thermochronology, which is dating when minerals pass through their closure temperature. Here's a general idea of what the closure temperatures are for different radiometric dating systems, with some of the highest closure temperatures occurring for the uranium lead system and zircon, some of the lowest ones for uranium thorium helium, fission tracks, cosmogenic isotopes, all under 100 degrees or so. And then with things like rubidium strontium on mica and argon-argon on mica being sort of in the middle at green schist to amphibolite facies. So what this means is that the three examples I gave you on the last slide are only technically geochronometers if the crystallization process occurs below the mineral's closure temperature. For uranium lead on zircon, the closure temperature is quite high. It's 800 degrees, so pretty much the system is always a geochronometer because the crystallization of zircon occurs below that temperature. For white mica, the closure temperature for the argon system is actually quite low, around 350 degrees C. So this means that if the recrystallization in deformation-induced recrystallization occurs above this temperature, say at 450 or 500, then the age that we will actually get is a cooling age, not a crystallization age, because the clock wouldn't have started until the system closed at 350 degrees C. White mica has a different, higher closure temperature for the rubidium-strontium system of 500 degrees C, so that system can be more robust at dating the timing of crystallization rather than cooling, because the recrystallization often occurs at green schist facies conditions below 500 degrees C. Sean will talk a bit more about this closure temperature concept in thermochronology as a tectonics tool, but it's important to understand the distinction between geochronology and thermochronology. They're used very differently to understand tectonic processes. So let's look at a couple example case studies in which some types of geochronology have been applied. Here's one for a suite of zircons preserved in a migmatitic rock from central Spain. A migmatite, in case you're unfamiliar with that term, is a rock that is hot enough to contain some partial melt. And these authors found 3 populations of zircon within these rocks and were able to date all 3 of them. One population they referred to as detrital zircons, in that all they had in them were igneous cores that predated any metamorphic event in the region. Another population, though, contained zircons with that detrital cores, but with distinct metamorphic overgrowths, and these tend to have a somewhat cloudy sort of microstructure that does not luminesce well. These images are cathodoluminescence collected on an SEM. And those metamorphic overgrowths have ages that range from about 350 to 323. The rocks also include a third population of newly grown, purely igneous zircons that would have been crystallizing within the melted sections of the rock. These have, again, these nice euhedral shapes and this well-preserved oscillatory zoning with ages that are concentrated at around 320 Ma or so. So these authors interpreted the suite of zircons to reflect progressive melting of these metamorphic rocks over several tens of millions of years, ultimately culminating in enough melt to generate new igneous zircon crystallization toward the end of the partial melting event. Here's another example, in this case focused on the rubidium, strontium, and argon-argon systems in white mica. And in this case, the authors were trying to pinpoint the timing of retrogression of these rocks from their peak conditions at eclogite facies. And to do this, they needed to pay a lot of attention to microstructural context such that they can distinguish the ages of mica grown early during prograde subduction from those that grew later. So the images in B through D, for example, are showing in situ argon ages on white mica, the red numbers there. And you can see in the backscatter electron image that many of the grains are actually zoned with dark cores and lighter rims, and that the dark cores are systematically older at around 65 to 70 Ma, probably reflecting the early high pressure metamorphic history, eclogite facies metamorphism. And then the lighter rims, they range from 60 Ma all the way down to the high 30s. So this is just another example of how we can use detailed dating techniques not only to demarcate the general timing of tectonic events, but also to track some of the durations that these events were taking place as they continue to grow and recrystallize new minerals with ongoing deformation and metamorphism. As a food for thought question, several of you taking this course are master's students working on a thesis project, or perhaps you're a bachelor student similarly doing a semester long project. It's likely that even if you're not working on a tectonics related project, that you're working with rocks or data sourced from a particular tectonic region and of a particular tectonic age or perhaps multiple ages. And if this is correct, then I suggest for Friday's discussion that you find out how the age for the rocks you're working on or for the tectonic province that you're working in was determined. So in other words, if you have time, take a look at how the ages related to your thesis project are actually constrained. In other words, which technique or techniques, are they cooling ages or crystallization, radiometric dating, or some other methods? I'd be interested to hear from you on that.